In this video, I will demonstrate how to create new custom standard drivers with ITNCM, IBM Tivoli Network Configuration Manager. Before starting the demonstration, I will provide some background on ITNCM drivers, and I will briefly discuss the information that should be collected in advance prior to creating a new driver. ITNCM ships with drivers for a large number of network devices. For devices that are not covered out of the box, ITNCM provides a wizard to create new custom standard type drivers. Standard drivers are CLI or command line interface drivers that provide basic configuration backup and configuration change functionality. New smart model type drivers cannot be created using the driver creation wizard. It is usually possible to create a new custom standard driver for devices that have a CLI interface that is directly accessible via Telnet or SSH. It may be difficult or not possible to create new custom standard drivers for devices that require navigating a menu to reach the CLI interface, or that make significant use of special characters in their interface. It is not possible to create new standard drivers for devices that only have GUI or API interfaces for configuration management. ITNCM is intended to manage network devices such as routers and switches, but depending on your requirements, it may be possible to manage specific aspects of other devices such as Linux servers. In this video, we will create a driver that can collect the output of a set of commands for a Linux server and that can execute simple CLI commands on a Linux server. The basic steps to create a new standard driver are the same for all device types with a CLI interface. Keep in mind that if you need comprehensive server management, IBM has products that are better suited for that task. In order to work efficiently when using the driver creation wizard, it is important to do some planning for your new driver. I will review the decisions you need to make and the data you need to collect before starting work on your new driver. First, what values will you use for the VTM OS, the vendor, the type, the model, and the OS version? You cannot use a VTM OS that is an exact match for a VTM OS that already exists in ITNCM. You should also consider how your choice of VTM OS will affect selecting devices and other ITNCM resources when using VTM OS filters. In this example, we will use a VTM OS of Linux Server CentOS 6X. It is possible for drivers to support multiple models and OS versions if the behavior and CLI commands for those models and OS versions are very similar. In this example, we will support one model, CentOS, and two OS versions, 5-star and 6-star. Next, decide how your new driver will verify the model and OS version information when communicating with the device. Typically, you need to identify CLI command output that contains exact or wildcard matches for the model and OS version strings. There are ways to map or replace strings found in the command output, but we will not cover that topic in this example. In this example, we will use the output of the command cat/etc/redhat-release, since that output contains matches for both the model and the OS version strings. You must know the sequence of prompts and responses used when logging onto the device. You will need to edit part of the driver to match some or all of that sequence. And finally, you need to decide what you consider the device's configuration to be. We need to be able to collect this data from the device and store it in ITNCM. In this example, we will capture the output of the commands cat/etc/hosts and netstat-nr. This slide provides the output of the commands used in this example for determining the device's VTM OS and for collecting the device's configuration data. You may find this data useful to refer to during the demonstration of creating a new custom standard driver. We'll launch the new driver creation wizard by navigating to the System Manager tab, the Drivers section, and then from the Tools menu, we'll select New Driver. When the new driver window opens, select IBM Templates, then select CLI-based via Telnet or SSH. We are not going to demonstrate creating TL1-based drivers in this example. Then click Next. And in the Driver Details panel, we enter the data that we decided upon earlier. So our vendor was going to be Linux, The type was going to be server. The model was going to be CentOS. And the OS was going to be 6X. The supported model would be CentOS. And the supported OSs were going to be 5-star and 6-star. Both the supported models and the supported OS values are comma delimited lists. We'll click Next to move to the Device Scripts section. Device scripts control the configurable details of the handshake between ITNCM communication handlers and the device for functionality such as logging on, executing commands, and transferring data. We're going to edit the SSH section of the device script since our Linux server only allows SSH connections. We will select an existing device script template by using the selection boxes near the bottom of the screen. In this case, we'll pick a Cisco, router 7200, and a version 12.3. We're using a Cisco router template because there are no VTM-OSs in ITNCM that have behavior really similar to a Linux server. And the Cisco Router 7200 family of drivers has an SSH connection section that will work pretty well without extensive modification. Note that if you have a custom device script that is closer to the behavior of your new VTM-OS, you can always paste in that script from the text mode of the editor. We'll click Open to load the device script, and once it loads, we'll make sure that we have the SSH tab selected and that we have the form editing mode selected. Advanced users may prefer to use the text mode of the editor. However, you must navigate the device script manually and be sure that you're editing the correct section when you use this mode. In this example, we're going to use the form mode. The first section we will edit will be the Connect section. This is the section that handles logging on to the device. We will use the information from the device logon sequence to edit this section. Since we are using SSH programmatically, it's likely that we will only need to know the prompt that indicates that we've successfully logged on, even though this section is designed to handle Telnet as well as SSH. We will also need to remove any extra lines that are specific to the template VTM-OS to avoid executing commands that do not apply to our target device. We'll first edit the script content to remove the if block that handles the enable command for routers, since this does not apply to Linux servers. Next, we'll remove the lines that control setting the terminal width and length on a Cisco router, since these also don't apply to a Linux server. Finally, we'll change our prompt from a # to a $, since in this case we're logged in as a non-root user and we'll be seeing the $ character as the last character in our prompt. Next, we'll edit the section of the script that parses the model information from the device output. We've already decided that we will use the output of the cat etc Red Hat release command to provide the VTM-OS data that will parse in this section. We'll edit this section to reflect the information from the output of that command. Note that in order to have a good match in this case, we've included a carriage return line feed character after the Red Hat release line that comes right before the CentOS string, which is our model, and we've also included a leading and trailing space after the word release. Next, we'll edit the section that determines the OS version. We'll click on the config.version tab and edit that information, also using the output of the command cat/etc/Red Hat release. The concept of feature sets doesn't apply to the OS versions of Linux servers, so we'll delete those lines. We'll change the rest of the lines to match what we see in the output of etc Red Hat release. In this case, we want to identify or parse out the string 6.7 as the OS version. So our find begin string will be CentOS release with a trailing space, and our find end string will be a leading space followed by an opening parentheses. Next, we'll edit the section that pulls what we consider to be our running configuration data from the device. We'll click on config.running. We want to send the command cat/etc/hosts and netstat-nr to the device. We need to edit the commands that we want to send in this section and the prompt that lets us know when we've received each command response. We also need to add information, strings to parse for, that indicate the start and the end of the configuration data. So we will paste in the commands we want to send first. Note that we are sending an echo command to output as a start marker. We'll use the echoed string as the find begin value in the upper panel. Note that we're also preceding this with a line feed character so that we can avoid including the actual echo command itself in our configuration output data. This is not required, having a start marker, and we're simply doing this to show an example of how this can be done. Also note that we don't put a final wait equals $. Remember, the $sign is the prompt we're looking for. We do not put a final wait equals $sign line at the end of this set of commands because we want to catch the final $ prompt as our config.running.end marker, both to tell us that we've received all the data and when we're parsing for the end of the configuration data. Next, we'll edit the information or diag section. We'll click on the diag tab. This section allows us to collect additional information from the device in addition to what we consider to be our configuration data. Unlike configuration data, historical versions of this data are not kept. Only one copy of this data per device is kept. The database field that stores this data is fairly large, but if the collected data is too large for the field, it will cause a driver error and the entire unit of work for the device will fail. We need to edit the commands that we're going to send in this section and the prompt that lets us know we've received each command response. We also have to add a string to parse for that indicates that we've received all the informational data. In this example, we'll send a single command /sbin/ifconfig. We'll also change our prompt that indicates the end of data to the $ character. Note that we don't have a wait equals $ because we want to intercept the final $ character as the end of our data. However, if we had multiple commands, as we saw before we edited, after each command except for the final command, we would have a wait equals $ line to make sure that we'd received all data from the first command before we started a second command. Next, we'll edit the device script section that controls sending CLI commands to the device using native CLI command sets. These commands can either make changes to the device or return data from the device, or possibly both. In this example, we are going to send commands to the device inline in the SSH session with the device. The section of the device script used for this purpose is the stream file section. CLI commands resulting from processing a native CLI command set are stored in a temporary file, and this section handles streaming the lines from the temporary file to the device. We will remove the existing commands that are intended for a Cisco router and replace those or leave only the commands that are needed for a Linux server. We'll also change the prompt we're waiting for to our $ prompt. Next, we'll edit global settings for the device script. We'll select the Miscellaneous tab. We'll change the prompts to match our $ prompt. And we'll add a line that strips the final line off the configuration data. This is an optional line. This line may or may not be useful to you depending on your data and whether or not a trailing line is a problem for your use of the configuration data. Next, we'll edit the config tag. Again, global data or global settings. We'll change the configuration type to single config since we don't have the concept of a startup and running configuration on a Linux server. And we'll change the prompts to our $ prompt, even though these values are probably overridden by specific script sections. This completes editing the device script, so we'll click Next to move on to the Resource Access or RAD section. Since we plan to use SSH to communicate with our Linux server, we'll select the SSH tab and make sure it's enabled. In the Transport section, we'll make sure that our streaming, put, and get checkboxes are checked. This is because we want to send and receive data over our SSH connection stream rather than creating an FTP server to send data back and forth to the device. In the SSH options section, we'll select SSH2 because our Linux version uses SSH2 instead of SSH1. There are no changes we'll make in the authentication section. In the command line, we simply make sure that we are using the SSH script type. In the configuration section, we'll leave native compare selected. We're going to turn off reboot on config load. This probably doesn't make sense for a Linux server, and we don't want to reboot our server unnecessarily anyway. We'll allow line by line for native command sets. This allows all commands to be executed in a command set, even if some of them error out, which may be useful when we try to collect information from the Linux server later. We're going to leave the compare device and ITNCM checkbox checked. For network devices, this box should always be checked for normal use. But if your Linux server responses are not consistent, this may cause ITNCM to incorrectly think that ITNCM and the Linux server are out of sync. In that case, we can edit the driver and change this setting. We only have a single configuration since we don't have the concept of a startup command with Linux, so we'll leave the multiple config compare checkbox unchecked, and we'll also leave the disable config checks on changes unchecked. This way, ITNCM will check to see if someone has changed the Linux server configuration outside of ITNCM before it makes a change. We're going to turn off pre-writes for imports and syncs. This is the equivalent of the copy running to start command for a Cisco router, and it really doesn't apply to a Linux server. We'll leave the report diffs checkbox unchecked for import. We'll still see any differences when we do a configuration synchronization. And we're going to leave the update on change check for our info, which was our diag section from the device script, and for configuration, so when we actually make changes, we'll get our configuration and our information updated. We'll leave the data type as CLI since we're just getting the output of CLI commands. Since we're not going to use the telnet and alt telnet access types, we'll disable telnet since we may use it later, and since we have no intention of having another access type, we'll simply remove the alt telnet type. This concludes the changes we need to make to the resource access document, so we'll click Next. We'll enter a description for the new custom driver. You should enter a description that's going to make sense to you a week, a month, or a year later when you come back to try to figure out what you created this driver for. The last screen simply shows us the details of the driver we just created, and we can always find this information later in the ITNCM driver management GUI. Now that we've finished creating our driver, if we refresh our drivers panel by toggling back and forth between screens, we'll be able to see our new driver in our top row with our Linux server CentOS 6X. And we'll notice that this starts with CST, indicating it's a custom standard driver. Now it's time for us to test our driver, try to actually import a device of this vendor type model and OS. Before we can do that, we need to add credentials for the target device into an authentication resource. We've created a custom driver test realm just to keep things organized in this example, and we've already created a authentication for our CentOS target device. You'll notice that we set the filter on this to Linux as the vendor, server as the type, and CentOS as the model, and we've left the OS version wildcarded. If we look at this, we can see that we just have one entry with our username, our password, and we've also set that password as the enable password. Although for a Linux server, we shouldn't need an enable password, we're just doing this to avoid a possible null pointer exception at execution time in case some routine is called that looks for an enable password value. Now we need to create a device of that type. We're just going to use the Linux server that ITNCM is running on, and we're just going to name it by its host name so we won't have to worry about name resolution. So we'll create a new network resource. We'll put in the IP address of our ITNCM server, and we'll select our new vendor type model and OS. We happen to know from looking at our Red Hat-release file that this is a 6.x OS version, but even if we pick the 5.x, at runtime, the parsing logic in the device script that we edited would find the right version and substitute that. Now that we've created the device, we'll import it to see if our driver works. Clicking on Import in the context menu opens our Import Network Resources wizard. We can see that our device is already selected, so we'll just step through the wizard. We're going to ignore errors. We've got an authentication resource, so there's no need to override the passwords. The priority really doesn't matter for the unit of work we're going to create, since it'll be the only unit of work running on our example system. And we'll schedule this for immediate execution, and we'll just give it a description. We can look for our unit of work in the Queue Manager and track its status. In this case, we can see that our UOW errored out. We'll take a look at the UOW log and get an idea what the problem is. In this case, it looks like there's a problem with our command to get the model section. We did something wrong sending the etc Red Hat-release command. So we'll have to go back and edit the driver and correct that error. We'll navigate back to the drivers panel, and from the tools menu, we'll select Edit Driver. This brings up our driver wizard again, and there's one driver we can edit, which is our new one. We'll navigate back to the device script panel, and we'll select SSH tab, and we'll go down to our model section. We can see that we left the equals out between the model.send and the command cat/etc/redhat-release. So we'll correct that. We'll check config version to make sure we didn't make the same error, which we didn't. Then we can click Finish, close our editor to save our changes to our new driver. And after saving our driver, we'll go back and we'll try our import again. And we'll check the status of our currently executing unit of work. And we can see that this time we were able to successfully import our device. Now we'll go and check the configuration data and the info data for that device. We'll have to use view native commands to see the configuration data, since this is a standard driver and there is not a GUI editor for the configuration. As we expected, we have our config start marker line. We've got the output of cat/etc hosts and the output of netstat-nr. If we look at our information data, that's under the hardware tab for historical reasons. ITNCM used to model hardware, and there was a GUI layout for the chassis. However, that work has now been deferred to ITNM. However, ITNCM still collects the text data in this section, and we can see the output of our /sbin/ifconfig command here. If the new driver fails when importing the device and a basic check of device connectivity, device logon credentials, and the accuracy of your device script editing in the new driver don't solve the problem, you can set the driver logging level to debug to get additional troubleshooting information. To do this, edit the driverlog.properties file in the config/properties directory under the ITNCM base install location. Near the top of the file, change the line log4j.rootlogger equals error, driverlog to log4j.rootlogger equals debug driverlog. Save the file and restart ITNCM. When ITNCM restarts, test your work against the device again. After that, review the data in the drivers.log file under the logs directory of the ITNCM base install location. Once you're done troubleshooting, remember to set driver logging back to error level to avoid degrading ITNCM performance. Now that our new driver is working correctly, to import devices into ITNCM, we need to test to be sure that it will correctly execute CLI commands from a native CLI command set. In order to do that, we need to create a native CLI command set of the same VTM-OS as the new driver. For our example, we've created a simple native CLI command set called getulimitData. The vendor filter is set to Linux, the type filter is set to server, and we've left the model and OS filters wildcarded since the command we're going to use will work on probably any Linux server. We can see that we're just going to send the command ulimit-a. The driver framework takes care of connecting to the device, sending this command, and detecting that the command is completed successfully. In this case, we're going to select a type interrogation native command set because we want to return results and be able to view those results. So our next step is to apply that command set to the device. We could apply the command set from the device or from the command set itself using the context menu, apply native command set. This opens a wizard. We can see that the command set is already selected, and we'll just walk through the wizard and select the device. We don't need to supply credentials since we already have an authentication resource. And we don't really care about the priority in this case since our system is not very busy. And we'll schedule this command set unit of work for immediate execution. And we check the progress of our command set in our queue manager. We'll look at the work currently executing and bore into our command set and take a look at the resulting unit of work log. We can see that our command set has completed successfully. It sent our command ulimit-a, and it got back the response we expected for a non-root user. This concludes our example of creating and testing a custom standard driver with basic capabilities to back up configuration data and to execute CLI commands. Although our example is for a Linux server, creating drivers for network devices requires the same basic steps.